I'd like to welcome everybody to our seminar this afternoon, and this is a great turnout. Thanks all for coming. This was a talk that was actually given 2 weeks ago at the NCAR directors meeting, and Jim Hurl was there, and he suggested that we do this as an all NCAR seminar, and obviously it was a great idea. This is a great turnout. So we've added a few more slides and expanded the talk. This is a talk that is sponsored by the Short-Term Explicit Prediction Program. It's a cross-NCAR program that Jenny Sun is leading, and you'll hear a little bit more about it during the talk. The speakers will be Jenny Sun, Rita Roberts, Dave Gotchis, and Barbara Brown from RAL, and Matt Kells from UCAR Comment Program. And I was going to make some other comments. I just want to make sure I got everything. Yes, the seminar is going to be webcast, so if you have questions, I'd like you to use the microphone so that the people listening to the webcast can hear. There are a couple of seats in the front here if somebody wants to try to sneak in. Bob, if you want to come up front, you can do that. Okay, I think we're ready to go, so without further ado, I'll introduce Rita. And she'll start it off, and then we'll have a sequence of speakers, and then we'll take questions at the end. Everybody's going to come up and be able to respond. So,
okay, thanks, Roy. Good afternoon, everyone. Thank you so much for coming so that we can share what we've been doing and also hear from you as well. I just want to begin by acknowledging this list of people here. Without their efforts, we wouldn't have been able to pull so much data together and do so much analysis already without their great efforts. So I want to acknowledge them up front. Thank you so much for your efforts. And why are we giving this presentation? Well, Roy has already mentioned this, but let me just review for you that under NCAR's Short-Term Explicit Prediction Program, the STEP program, we've been conducting research on developing an end-to-end hydrometeorological prediction system for the Rocky Mountain Front Range. And a key goal of this STEP program is to provide improved prediction in the location, the timing, and the intensity of heavy rainfall, and to provide improved flash flood guidance. So this is what we've been working on through the program. And then when the flood happened, then we realized we really need to get on this and start to collect data from this very extreme event. So we've been working to gather a lot of the different data sets. We've been running it through the components of the hydrometeorological prediction system. And up here you see are the components of the system. And as we present today, we're going to be talking about the data in context of these different components of the system. And as Roy mentioned, we presented some highlights and preliminary findings to the NCAR Directors Committee meeting a couple weeks ago, and we were asked to give this seminar as a follow-on. So I'm going to begin by talking about some observations. Many of you, being meteorologists, probably know that the synoptic environment on this day, or during the week, was we had this upper-level low-pressure system in the southwest of the U.S. that was circulating and persisted throughout the whole week. And it acted to bring a lot of southwest monsoon moisture up to the Colorado, northeastern Colorado. And in addition, we also had at the low levels in Colorado southeasterly flow, bringing high-level moisture into the area, creating a lot of upslope flow along the foothills, and producing a lot of the heavy rain that we saw. So we had two important features going on during that whole week. And some of the heaviest rainfalls, you'll remember, actually occurred between Wednesday afternoon and Thursday afternoon during what looks to be two intensive rainfall periods. The first intensive period seems to have been associated with this very tropical-like regime, this synoptic regime. I remember on Wednesday watching the rain falling, and it was intermittently steady rainfall, then heavy downbursts embedded into it. No cold outflows, no cold pools, very warm. The temperature stayed around the 60s. So very, very tropical in nature. The drops were generally small. indicative of warm rain coalescence processes associated with some tropic-like rainfall that we see in Hawaii and other areas in the tropics. The second intensive period actually seemed to have aspects of both tropical and more continental-like weather regimes. And by continental, I mean more like the type of weather we normally see in Colorado: mixed phase, ice, graupel, a spectrum of water droplet sizes from small to large. So definitely a couple of different regimes may have been in place. This is something that, of course, requires further analysis. But this plot here, you can see it's a plot of precipitation accumulation totals for the whole week. And what we can see here is that there were, appears to be, 2 different intensive periods of heavy rainfall occurring, all within the 24-hour period, again from Wednesday to Thursday. And you can see that the precipitation totals went, and this is at the Marshall Field testbed site, so there were 6 different rain gauge sensors that were out there recording. And you can see that the rainfall accumulations just during the period of 24 hours went from 60 millimeters up to 250 millimeters, or about 10 inches of accumulation just in that one period. So a phenomenal amount of rainfall occurring. And again, this is just one site at the Marshall Field site. So here is a loop. This is, again, during that same period, a loop of the radar reflectivity from the Denver radar. And so as it loops through, you can see a number of features during this event. You see embedded cellular precipitation cores of heavy rain. You see linear features here. You see the widespread stratiform precipitation that occurs all along the Front Range during the later period of this time. Also, what we see in here is the surface station data, and we see that we have the easterly, generally easterly, southeasterly flow occurring into our Front Range region. But we also see that the winds are tending to rotate, and even as you look at the precipitation data, you see that there's a implication of rotating precipitation with those wind fields. So a lot of interesting features going on in the data, and very variable. So if we look at the COCORAS plot, now COCORAS is the voluntary network of community observers. This is just a 24-hour period of rainfall observations, rainfall accumulations for ending on Thursday morning. And this shows the high variability in rainfall that occurred along the Front Range. You can see some maximums that occurred in Aurora, east of I-25, and of course along Boulder County. Matt Couch will talk more about the precipitation amounts later, what was actually recorded. But a lot of variability, and when we collected this at that time, the official Boulder total was 14.86 inches of rainfall as of that Friday. Okay, so to be able to really predict heavy rainfall, one of the most important aspects is to be able to get our estimation of the rainfall correct. And one of the tools that we use heavily to do this is radar data. And using radar data, we have the reflectivity, and we can compute a rainfall rate from that information using different types of ZR relationships. And this one here on the left is one of your more typical standard relationships. And here on the right, we've run the data through with using a tropical rainfall rate, ZR relationship here. And you can see right away the difference. In the more typical standard relationship, it was largely underestimating the amount of rainfall in the whole area. And here's the Front Range region. However, the tropical rainfall relationship did a really good job. And maybe that's not so surprising, because what we were seeing was very tropical-like weather. And small weather, a lot of small drops, large concentrations of small drops. Now, the Denver weather forecasters, they had the option to see several different QPE fields when they were on shift. And they ended up using a relatively new QPE field. That's the dual polarization QPE field, which is shown up here. These two plots were just generated for 1 day period. This is a 5-day total accumulation, and it's in inches. So don't try to compare these plots. But when I had talked with them, they had commented that they felt the system was very tropical in nature, and they actually thought about running the tropical ZR relationship instead and going with that. But they pretty much stuck with the dual pole estimations, and they weren't too bad. They did a reasonable job. Still a little bit underestimating the precipitation.
What were those numbers?
Up here, so the red is about 10 inches, color scale here. Yeah. Okay, so why am I showing you this? Well, the purpose is that there's still a lot of research to be done to get the best QPE. For the forecasters on duty, they have to decide which one to go with and which one to use. And so being able to automatically produce the appropriate relationships for forecasting in a hydrological system or for the forecasters is one of the challenges. And also being able to choose the correct one for the meteorological situation is also very challenging. This is part of our research. Now, you probably are aware that the radars have been installed with dual polarization capability across the U.S. And for some of you, you may not know why that's important. Typically, the radar, it provides information about storms and where they're located. But what you gain from these dual polarization fields, and this is just an example here of a differential reflectivity field for the same time period, is you gain more information about the drop sizes. How big were those drops? Was there ice crystals in the clouds? And so what we see here is that on this particular day at this time, this was at midnight on the evening of Wednesday evening, midnight, we see that the drops were primarily small drops in these storms, ranging from 0.3 millimeter to 3 millimeters in size. So this field is very important. We'll be looking at this quite a bit, the dual pole fields. Also at the Marshall Field testbed site was a Parseval disdrometer. Paul Kuchera was running this, and these are just some plots from that. It not only gives you total accumulations, which it recorded 352 millimeter accumulations, but you also see what the 1 minute rain rate is too. For example, here on Wednesday evening, we see how much rain was really falling. And what's also nice about this instrument is that we can also get information about the different drop sizes, and that will be work that's ongoing to see how those drop sizes compared throughout this whole event for the different weather regimes. Okay, so I've gone from QPE and skipped over the forecasting and I'm going to talk just a little bit about the nowcasting. And when Jenny comes up, she's going to talk a little bit more about the NWP, as will Dave as well. But what we saw when I looped the radar data, we saw that it was very variable in nature between convective elements, linear, stratiform. And it's really important to be able to capture and be able to forecast where the heaviest rainfall is going to occur, and especially in a situation like this that was so variable. So what we see here during that same 24-hour period is I've just noted where the convergence is of some of the larger scale, or what I would say mesoscale convergences. And you can see how it evolves during that period. And you can also see how the precipitation, where some of the heaviest rainfall is occurring, is related to where those convergence regions are. So we need to be able to predict the changing wind flow in the boundary layer and the changing attributes of the storms themselves in order to get this right. This is just another example here where we had actually even smaller scale convergence feature that was evident not just in the surface station data but also in the radar data. And within an hour and a half we see that there's a lot more development of heavy rainfall and storms in this area. So it's really important for us to be able to pick out these attributes for prediction of the heavy rainfall locations. And then this is just one last slide that I wanted to show you on the topic of nowcasting. This is, again, at midnight on Wednesday, where we're in this heavy, intensive rainfall period. And the interesting thing about this is that Boulder was getting some of the heaviest rainfall at this time, right in this area. The reflectivity was only about 45 dBz, which is on the low side for us in Colorado, but more representative of this tropical-like nature of the system. And if we look at the radial velocities, or the wind field here, what was happening at this time period is we had a lot more convergence into the storms that were along the foothills here of the Front Range. And also, a very interesting feature, that we had a rotation within this storm showing up here. So there was quite a bit of heavy rainfall. We also saw that this was the only time period during the whole event when there was lightning occurrence with these flooding events. And also I wanted to show you that the storms typically were not very deep compared to what we normally see here. This was probably the deepest storm we saw, of 10 kilometers. More typically, the storms were running around 8 kilometers deep. Again, very shallow, very maritime-like storms that we were having here. And I think, again, that's all I want to say, just the importance of being able to nowcast all these more smaller scale phenomena. So now I'll turn it over to Jenny, who's going to talk about the NWP.
Rita talked about observations and QPE, and she also talked about in some aspect of nowcasting. In this part of my talk, I'll focus on NWP and nowcasting. Well, in recent years, actually, NWP and nowcasting are getting closer and closer. They're merging. So it's very difficult now to say which is which. All right. Okay, so I'll look at this precipitation in a different way, slightly different way. So this figure shows a domain average over a domain that covers Boulder and the Denver areas. It's a 1 hour rainfall plotted for this 5 days. So Rita already talked about this 2 intense periods. So you can see if we plot this way, that's how they evolve with time. And I'm going to also focus on the intense period 1. You can see that in this period, if we plot this 6 hour accumulated rainfall, then we can see clearly the center is in Boulder. And also in this 6 hour accumulated rainfall, then in some spot of Boulder, the rainfall can be over 200 millimeter. That's equivalent to 8 inches of rain. As we will see from next slide, that forecasting the heavy precipitation in the intense periods is challenging for NWP models. Okay, we ran the WRF model, but after the event, of course, with the 15 kilometer and 3 kilometer nested grids, initialized by GFS analysis. GFS is US NCAP's global model. Okay, so we initialized the model at 12 UTC on September 11th. As you can see from this plot, this 24-hour accumulated rainfall from WRF 3 kilometer forecast actually captured the large-scale pattern reasonably well. I really believe this kind of forecast can be useful for the forecaster to use as a guidance 1 or 2 days ahead of time. But if you look more closely, of course, it misses several small-scale details, and especially the high intensity of the precipitation. So that the high intensity and the small-scale feature is really responsible for the heavy rainfall and flash flood. All right, then we ask a question, what are the mesoscale features that might have been missed by the NWP models? And we have this system called VDRES, Variational Doppler Radar Analysis System. It's kind of a state-of-art system for high-resolution, rapid refreshed analysis. So we ran this model for 4 days with a 2-kilometer resolution, simulating the 2 radars over this domain. One is located at Cheyenne, the other is located at Denver. And VDRES use the 4-divar technique, so it has a class-scale model that can has ability to assimilate radar observation and also retrieve the unobserved meteorological variables. The analysis can provide vital information for observation-based nowcasting and model initializations. Okay, here is a movie loop that shows it's a 10-hour movie loop, continuous analysis with an interval of 15 minutes. So that covers this period, a very intense period. If you still remember, that's Wednesday night. So that's starting from 4:30 p.m. to the early morning 2:30 a.m. the second day. So it's marked here. That's the period. And you can see this is the front range above 2,000 meters. And the red shades are the observed reflectivity greater than 25 dBz. But mosaic, this is a mosaic between using the Cheyenne radar and Denver radar. So it's not just from one radar, it's 2 radar mosaic together. So there is a little bit of smoothing effect when we mosaic it, but it's real observation. Okay, so now I'll show this movie. And
what's the time step of the?
15 minutes, yeah. So, okay, then I will run it another time, but and just stop a little bit. That's what I see from the VDRES wind analysis. It reveals that enhanced the southeasterly flow by a mesocyclone. Actually, Rita already pointed out this circulation here. Then it also shows an intensified northeasterly flow near the Colorado and Wyoming border. And both flows merged in Boulder and Larimer counties. So let's run it again. See if you see those features. There is actually a sudden onset of a northeasterly flow.
What are the magnitudes of the wind?
The rain, it's starting from 25 dBz. The highest one is over 40. It's a pink. The wind is here. 10 meters per second is like this long. Yeah, it's many places over 10 meters per second. Okay.
I'm sorry, what level was that at?
It's 150 meters above ground. So that's why you still see the vector over the mountain. It's above the ground level, 150 meters. Okay. So of course, this is the first run we did. In order to resolve some more detailed feature, then we need to maybe run even higher resolution. But we plan to use this wind analysis, along with others. VDRES can also produce temperature and humidity analysis. Then all this analysis can be used in the automated nowcasting system, like NCAR's auto nowcaster system. We can also use them to initialize like a WRF model. So we get a better initial condition with the hope that we can improve the very short forecast to be able to capture all those small scale features in the model. Okay, so here is a wrap up of my part of the talk. We all see that the current new NW models are able to give some guidance maybe 1 or 2 days ahead of time, but they cannot resolve the small scale features, so they cannot do a very accurate and location specific QPF, which is required by doing a very good flash flood prediction. So basically, we believe this is a nowcasting problem because if we cannot do the first 6 hours right, then we have no hope to do a longer term forecast. But however, we also know this is very challenging. Much research is needed. And the success of nowcasting critically depends on the optimal and timely use of high-resolution observations, such as those from radars and bassinets, through rapid update data assimilation, and also through the optimal blending with an ESPER system based on some conceptual models. And we plan to run our high-resolution WRF model with the capability of assimilating radar observations in the future. Of course, we don't have time to do that yet, but we will run that to see how much we can improve the rainfall forecast. If we can do more location-specific, timing-specific, and with a better intensity. And through the NCAR STEP program, we are doing active research toward the improvement of 0 to 6 hour QPF. And we've already planned for next summer a real-time demonstration that it will have all the pieces you hear from today and in our front range region. Okay, that's
So now I'm going to talk a little bit about ideas about evaluation of these kinds of forecasts. And the evaluation piece is a very important part of the whole overall STEP program, at least this end-to-end flood forecasting system that we're developing. So we really haven't done the verification of the forecasts that you've seen yet, but we are starting to think about the challenges that we have because it is a very challenging problem to evaluate forecasts like this of really extreme weather. So I'm going to just talk about some of the issues and some of the things we're trying to do to resolve those. And a lot of those issues have to do with both the methods that we use for verification and for evaluation, as well as the observation systems themselves. So some of the challenges just in the verification error is that when you're dealing with extremes like this, the representativeness error between matching a model grid to an observation can be particularly significant. So there's a lot of uncertainty introduced just simply due to that. And spatial errors can be even more significant than they are in our standard verification approaches, which leads to inappropriately poor scores and uninformative information coming from traditional methods. So we have to look at different ways of evaluating these kinds of forecasts. And there are huge observation challenges. You've seen a number of different QPE images already, but I'm going to show you a couple more. And we have the problem that the observations may not really be able to express the extremeness or represent the actual extremeness of what we're seeing at particular locations, particularly when we're looking at an analysis field. And the observation errors can also be extremely significant, but are not necessarily accounted for when we do an analysis and create a QPE image. And again, the analyses, as we saw, there can be very big differences between the ZR relationships and what kind of QPE comes out of that. So there can be very significant differences in the verification results depending on what QPE you use. And then for stream flow, we may have censoring of the observations simply because the gauge may be overrun and that information has to be recreated in some way. So just a little bit on the verification issues. This is the only slide on that. One of the approaches that we will be taking with these forecasts is to apply some spatial methods which take into account some of those issues of of having small displacement errors create huge misinformation about the quality or usefulness of the forecasts. So this is an example from another very extreme weather event, and the traditional scores that you see here, if you're familiar with traditional verification, actually make this forecast look really, really bad, even though it's actually a pretty good forecast from a visual perspective. And if we apply a spatial method, such as the ones that we'll be applying in looking at the flood case as we get further along, you can see that you can get a lot of information about what exactly was going wrong with the forecast in terms of, for example, the intensities being close, but the areas maybe being a little bit too large. And in this case, I'm just focusing in on this red area up here. So we can get a lot more information from looking at those kinds of things, and we'll be applying those kinds of approaches. Now to talk just for a minute about some of the observational issues. This is an example of two different estimates of QPE, and these were for basically a two-day period, a two-day accumulation. The Q3 is a radar-only product. In this case, they actually have a multi-sensor version, but this is the radar-only version of a QPE that's produced at the University of Oklahoma. And you can see very big differences between that and the stage 4, which is the same QPE that Jenny was showing. That's a gauge-corrected radar image, where in the gauge-corrected stage 4, we're seeing large areas of a very significant precipitation that is not showing up in this. It's a fairly advanced technique, the Q3. So this suggests that the choice of QPE would have a huge impact on the verification results. So we have to somehow come to a rational decision about what QPE is the appropriate one. And it's pretty difficult to figure that out in some cases because we don't know what the right answer is. And some models will do better with Q3. If you had a model that was underestimating precipitation, you'd probably like to evaluate it with Q3. But others that actually are able to produce more precipitation would show better results with the stage 4. So examining these differences in QP is going to be very critical as we go forward, and the selection of the QPE that we apply will be essential. I want to show another example of QPE. Again, this is the Q3 from University of Oklahoma. And this is actually off of their website, which you can go to yourself and go look at different QPEs that are available, compared to a hybrid dual pole that they also produce there. And again, you can see these same kinds of differences. These are for 24-hour precipitation estimates. I think it's for the period ending at about in the morning on the 12th. And one of the nice things I think that's very illustrative of some of the issues is a difference plot, which you can also look at, which shows the large differences in QPE values produced by these two. This is the Q3 minus the hybrid dual pole, and you can see negative differences of about -2 inches here, and some small areas where the Q3 was actually overestimating, and I'm guessing that those are places where the precipitation was misplaced. So now I'm going to ask Matt to come up and talk some more about some of the issues with observations.
Thanks, Barb. So I have 3 slides, and I want to talk specifically about the observations, as Barb started talking about gauges, as well as what happens to the water once it's on the ground, the hydrology and the river flows that come out of that. I am one of the 2 cooperative observers in Boulder. The Cooperative Climate Station is on the NOAA property. This photograph right here, taken by Bob Henson, is of me doing the 9.08 report as of 6 p.m. On September 12th. The previous daily record in Boulder was 4.80 inches, so really a big difference the way we clobbered that old record. I am also the coordinator for Boulder, Broomfield, and Gilpin counties for COCORAs. These are the COCORAs gauges here, if you're not familiar with that. They're the 10-inch high, 4-inch across plastic gauges. And these are very valuable as we do our rainfall analyses, but we have dozens of people across the Front Range. And just Boulder County alone, actually, we have dozens, and all the other counties as well. There are a lot of things, though, that we've been doing since the storm. There are errors and sighting problems that come up when we have a big event like this. We don't want to have a new state record be something that we haven't really verified was truly an accurate report. So I've been working with Nolan Duskin at the Climate Center up at CSU. We're going through hundreds of reports. He's doing more of it. He has some people working with him, but I'm going through all the Boulder and Broomfield County stuff. And some of the things I've identified in this county for some of the big reports, there were some people that were much too close to buildings. They were probably getting splashed off the roof. Some of our observers have been doing it for 10 years and their trees have grown up. So there were a couple cases where a gauge was directly under the bough on the edge of a tree, so that would enhance the precipitation. People spilled some of the water when they were measuring. They're not used to having that much water in a gauge. It's never happened before. And in a few unfortunate cases, they go out, they're all excited. The gauge, this thing is nearly, full to the top. It's a lot heavier than they think. It's wet. They pick it up and dropped it and splat. It's all over the ground. So there were a few incidences of that. There are people that had automated gauges. They're not part of COCORAS, but I've been trying to get whatever we can out there. That's useful information. The problem is if it's not calibrated, automated gauges provide really good time resolution. They don't necessarily provide the best accuracy. So we're looking into all that. The official analysis of rainfall is not out yet. I just talked to Nolan again today. But this is the preliminary, and it doesn't include that bullseye down in Colorado Springs. We will include that in the official analysis. And this is for the 1 week period ending Monday morning at 7 a.m. And you could see in Boulder, the whites here are over 17 inches for that week, and you see how it extends northwest. Now notice up here, there aren't any reports. I know you can't read the numbers, but you could see where the gauge sites are. This is something Nolan is actually contacting people that live here just to ask, did you record any rain? Some of them, of course, aren't living there right now because they've been evacuated and can't get to their homes. But we believe that there may have been heavier rain up here than this analysis shows. There's a 17.77 here near Allen's Park. That's one of the people that spilled some. So that's a minimum of what he reported. So that's what this looks like. One of the things I want to point out is this is going to be useful when Dave talks about some of the hydrologic forecasts. Because the intense precipitation was angling to the northwest, when you think about Coal Creek and Boulder Creek, the upper part of the drainages was actually above the most intense rain. But when you go further north to the St. Vrain drainage and the Big Thompson, those rivers, their mountain watersheds were in the most intense rain, and they appear to have had much more severe flooding than Boulder Creek or Coal Creek did. Boulder Creek, and I'm going to get into this next, the flows or the discharge is the other important measurement. And those aren't final yet either. Preliminary, it looks like Boulder Creek at Broadway was maybe 5,000 cubic feet per second, CFS. The 100-year flow estimate is 12,000. So we were well below that, but again, the final numbers on that are still to come out. So I want to talk a little bit more about flow. There are two ways that we measure what a river is doing. The one that's more intuitive to most people is the stage height, how high the water is. But the most important measurement is the flow or the discharge, which is, as I said, CFS, cubic feet per second. And there's usually a nice relationship between how high the water is and what the flow is. So if the water is 5 feet, the stage is 5 feet, you might have 300 CFS. If it gets up to 10 feet, you might have 1,000 CFS. Boulder Creek at Bankful is 1,000 CFS. The problem is once you leave the river, when you're in flood, that clean relationship goes away. Now the water is filling up areas, it's following the road grid, it's taking water in from the road grid, it's going down ditches. We have a lot of agricultural ditches across Boulder. It's filling up basements. All this stuff is part of what's coming down. Oh, well, that is part of the flood. And so what the USGS has to do is they go out and they look for high water marks, do cross sections, estimate how fast it might have been moving to get what the flows actually were, what these peak discharges were. And that's going to take a little while, but they are actively working on that. Well, I don't know if they're actively working on it this week, but some of them are probably actively working on it illegally, but that's being done. So just to give an example of that, this is the Big Thompson River. This is from the Colorado Air Patrol. This is just above Drake. Drake is right here. So this road is where the North Fork comes in. And one of the things to point out, here's where the road is. So the river rechanneled itself, took out the road. The old channel, I think, was right here. So when we estimate the flows, when the USGS does, they do this cross-section of the damage and they come up with high water marks. Closer to home, I took this photograph looking west toward Broadway. Judging from the debris lines, the water was already down about 1.5 feet from its peak at this location. This is where White Rock Ditch takes off from Boulder Creek. The gate was up to stop the water from going in the ditch. You could see how well that worked. But when you do, and that's the thing, you know, a lot of times when people have ditches going through their backyard, they're told by the city, well, this is a controlled ditch, so you don't have to worry about it. But they're only controlled when the river isn't in flood. If the river is in flood, then the water finds its way there. So when we do the discharge measurements, this water here, which is not in the creek anymore, it left the creek, is heading down, and that's part of the volume that has come out of the mountains, and it has to be included. Some of it actually rejoined the creek down near Arapahoe, but that's why it gets very complicated, and it takes a while for all these measurements to be done. I expect the official measurements of flows and the final rainfall analysis to be done this month, and I'm hoping to give another talk focusing specifically on that sometime maybe in a few weeks. But right now we're going to talk about the hydrologic response, and it's Dave's turn.
Thanks, Matt. That was a perfect segue to talk about some of the hydrological modeling work we've been doing associated with this. So those of you who have worked with in the past and have followed some of this research, we've been doing some modeling and model development activities here in the Front Range for several years now, since about 2008. And this is the domain we've been using for evaluating a lot of different precipitation products, a lot of forecast products, and doing a lot of model evaluation work. So I'm going to breeze right through a lot of the issues related to the description and actual application model, just get to some of the results that we had for this past event. So we've got this model. It really runs over a fairly extensive domain, about 268 by 260 kilometers, which is really nothing. It's about postage stamp for your typical NWP model. But for a distributed physics-based hydrological model where you're doing a lot of the processes at 100 meters, it tends to be a little bit more ambitious problem from the hydrologic perspective. So we're taking a lot of the forcing data that we're getting from these atmospheric models, the numerical weather prediction models, the nowcast, and the radar estimates of rainfall, the QPE products, and putting it into this domain at a 1 kilometer grid, and we're able to intercompare a lot of these products. And then we're doing, like I said, the routing of these processes, so the movement of the water across the landscape and through the channels at 100 meters. We have a pretty dense channel network. I know the folks in back, that might be a little bit of a blue blur. But essentially, we use a threshold for starting a channel. It's a whole geomorphic area of research as to what defines a channel. We're not going to get into that here. But we start a channel after about 1 square kilometer of contributing area. So we're really able to map a lot of the convergence areas and ways that the water is collected on the landscape and pass it down this network. And in addition to that, we're focusing on the analysis of flow at 61 different stations. Most of our work in the past has been associated with foothill and higher elevation watersheds, and that's what you see predominantly mapped out here. Little by little, we're getting more flow information and more experience in working at the stations out on the plains, but we have relatively less experience with that at this point. Okay, so what I'm going to talk about here is really some of the inner comparisons of running some of these different precipitation products and one forecast, which was running during the event, through the hydrological modeling system. This is a figure that was similar to what Rita showed very early on in the presentation, which is the estimate of rainfall, about 2.5 days of accumulation. The color scale here ranges from 0 to 15 inches, where the red is the 15 inches, using this tropical rainfall rate radar reflectivity relationship. So we can see where that maps out in some detail across the mountain front here, looking at, this is essentially the Flatirons right down here, moving northward and then across over James Creek, Left-Hand Creek, on up into the South St. Vrain, Middle and North St. Vrain basins, and then up into the Little Thompson and Big Thompson drainages. If we overlay this again compared to the standard ZR relationships that's used for analyzing and estimating rainfall in this region, as a default, it often gets tweaked during operations, but as a default, we see this rather large discrepancy. And so we're going to look at some of the contrasting hydrological model behaviors forced between those two products. This right here is a snapshot basically validated at September 12th at 1:15 in the morning. So right when we were experiencing some of the heaviest flash flooding flow events during that period of time. And what you're looking at then is a color coding of stream flow values across these channel networks, zoomed in here really right to Boulder County. This is the boundary between Boulder and Larimer County right here, and you can see the shaded mountain fronts in the back, and see a lot of these high intensity flood values moving downstream. Now, unfortunately, I didn't put this in CFS, it's in CMS. I apologize for the metric use, but we're looking at flows which range from 0 to 50 cubic meters per second, which ends up being about 0 to about 1,700 or 1,800 CFS. And many of these values are well over the maximum scale here. I've labeled the canyons here as well, the major creek systems that you can see. And so one of the things that we're excited about using these kinds of tools in difference to some of the more historic or past ways that we model hydrologic behavior is this ability to resolve all of these tributary systems, all of the minor creek systems, which in this case weren't so minor. And that's where a lot of the more severe flooding actually occurred. Areas like 4 Mile Canyon Creek coming out of the foothills in North Boulder, areas like James Creek and Left Hand Creek coming here into this area. So I'm going to show a little movie of this. This is an animation. I've had to strip it down just for file size issues, so you're going to be looking at hourly time steps of flow. Whoops, maybe I won't. There we go. And you'll see the flood waves emanating in the source regions right along the mountain front. I'll play it again in here in a second. It's going to spin through about a day and a half, so you'll see a second wave of precipitation come along, which is a little lighter than the first wave, but did have some significant impact. And you'll see, again, when I replay it, the brightest colors are emanating out of that swath running from southeast to northwest that Matt just talked about. We'll run through it one more time here. So really the power of, we have a whole set of issues related to accuracy. How good are these? And I'll show a few examples of this. And we've got some hits and misses, strikes and gutters. But beyond the accuracy issue, the other part of this is what value we get out of this. Even if there is some bias or some error in some of these, we're able to provide quantitative flow information, and at least at a relative basis from background flow values. And a lot of these systems which are either not captured in more lumped hydrological modeling systems or not even observed, and hopefully be able to provide warning information on that. Okay, so just a snapshot of some of the more heavily impacted areas. There's 4 stations here. I'll show some verification plots here for. This is James Creek up above Jamestown area. So this was a little bit higher elevation. This is the Rowena station, if folks know where that is. And in terms of flow and timing, we're okay, and the relative peakness of that event. The red is the observed flow here, and the black is the modeled flow. And I apologize for folks in the back. The black may be a little hard to see. A little bit of overestimate, according to the gauge estimate there. Going to lower Left-Hand Creek, basically where Left-Hand Creek comes out of the mountains, we see the evidence of what Matt just talked about. The red, again, is the observations, and this is where this station essentially got blown away. So there was no further observations. It actually stopped reporting for a little bit because it exceeded its empirical relationship between that flow depth and the discharge, and so they put an error on it at that point. But eventually, we do know that the station did get destroyed. So we're going to have to essentially rely on surveys conducted by the USGS, the state of Colorado, and other entities, probably some folks here in this room, about what that peak flow value was on this system. We don't know at this point in time. This is coming out of 4 Mile Canyon at Logan Mill, for those folks who know that area pretty well. Red, again, is observed. The model was a bit aggressive here, and it's not surprising. We implemented a set of parameters for 4 Mile Canyon, which had burn impacts on them in 2011. And we did a lot of work on that event with folks at NOAA, Rob Cifelli, and folks up at CSU, looking at rainfall estimates and runoff from the 4 Mile Canyon burn. And we feel like we got a pretty good representation, but we haven't evolved those parameters at all since then, and we know that there's been a significant amount of revegetation in that area. So we're a bit ambitious coming out of the burn area with the flow here. Lastly, Boulder Creek, right above town, where the Highway 119 goes across the creek there below 4 Mile Road entrance. And again, you can see a bit of underestimate in the flow estimate here Observed flows there were about 3,000 CFS, and we only got about 2,000 CFS, but the timing and the relative impact of the storm flow on this was reasonably well simulated. I want to focus in on this QPE issue. So all of those were performed using that tropical ZR, which essentially within 3 days after the event, we were like, okay, this thing seems to be validating anecdotally pretty well when we overlay some stations with it. But that's not necessarily what's available in real time. So let's look at what happened in the lower St. Vrain Basin, which is the contributing area, of course, to what flowed through Lyons. And so this little area in orange here is essentially the St. Vrain Basin below the peak-to-peak highway and between Lyons. So this is going to be accumulated rainfall plots from 4 different quantitative precipitation estimate products. This is the default NEXRAD that's shown here, and we're showing a maximum of about 75 millimeters, basin averaged over that basin. So it's very low compared to what we know happened based on gauge data. This is that Q3 radar product, radar only, which comes out of the folks from University of Oklahoma and NSSL. This is the stage 4 gauge corrected product, so quite a big jump up here, looking at about 160 to 170 millimeters basin average precip. And basin average will tend to dampen those maximum values that you'll see in gauges, so we won't ever get those really big ones. And that's the tropical ZR relationship. So a massive uncertainty in the estimates of rainfall, okay? The only thing that is potentially not available in real time here is the stage 4. So if we take that off the shelf and say we can't use that, that comes a day or two later, these 3 products are sort of our operational uncertainty with radar-only estimates of precipitation. It's massive, okay? If we look at just that's the accumulated values. If we look at the peak intensity values, you can see that peak intensities, again, basin average, so these won't be really dramatic numbers, for 30 minutes are ranging from about 5.5 millimeters per hour up to about 20 millimeters per hour. So a 4-fold increase, more or less, in peak 30-minute rain rates. And as most people who study flash floods, as well as most all people know, it's that intensity which can have a really big impact on the flash flood response. So what happened in the modeled stream flow then at St. Vrain, the St. Vrain at Lyons? Well, this is the simulation that we had of that system using the tropical ZR relationship. And here's where the gauge blew out in Lyons. So again, we're waiting to see what the peak is. Talking with Matt and other folks from the GS who are involved in trying to reconstruct this flow, it's probably going to be quite a bit higher than 4,000 CFS on the St. Vrain. So the model was underestimating it here. If we go use our default ZR, no flow was produced in the model. No storm flow, okay? It's not total stream flow, it's storm flow. It's the quick runoff response from the model. We can get into what that means, but really because of those very low rain rates, no more than about 5.5 millimeters per hour basin average coming off of this. No rainfall, no runoff was represented. For the hydrological modelers who like to discuss calibration, we've done some work in this area. This is what the model has been largely calibrated to. Okay, so this isn't really a, play the shell game and switch and say, okay, there's a different response. Most of the events that we get around here, this ZR relationship works pretty well, and so that's what we had calibrated the model to. Not for this specific basin, for regional, for other basins, and then we regionalized our parameters. But it clearly wasn't an appropriate estimate of rainfall in this case, and it clearly had a bad stream flow response. This seems to be a much more realistic depiction. Okay, like I said, we ran the model actually operationally, and we were ingesting data from the North American model, which is the national mesoscale model, 12 kilometers. And I just wanted to show this as an example to illustrate some of the issues that we had. And so what I'm going to step through is a series of 24-hour accumulations from different initialization times, which will be listed right here. And these are 24-hour accumulations, and our scale is 0 to 50 millimeters, so it's even not that much. If Boulder sits right here, we're in the donut hole. And if we step through most of these forecasts, right? Actually, I was a little further south, sorry. Boulder's going to sit right here. So we're still in somewhat the donut hole. It's largely missing in those 3 forecast cycles, and it doesn't really improve for most of the other forecast cycles around that period. The bullseye of heavy rainfall, or that trending heavy rainfall that went from southeast to northwest. in this area. We do have heavy rainfall in the region, so from a larger scale perspective, it really wasn't too bad of a forecast. But for hydrologic applications, we had some issues. Again, just a snapshot of the flows that were produced by running those precipitation forecasts through the hydrological modeling system. Yes, we got flows, particularly up in the Big Thompson, where there was some heavier rainfall in the model, and then out east. But really, a lot of the front range canyons were lacking in a flow response. I've rescaled the colors here just to be completely honest so that you could actually see these in some way. But really, for hydrologic applications, we have to have some improvements in the NWP forecasts. All right, so let's wrap up. Obviously, what you've seen today is a lot of work in progress. There's a lot of different things that are going on, and we know that a lot of other groups are working on this, and we're collaborating with a lot of those groups. So we're really trying to focus on what some of the principal sources of errors were, where did we go wrong, and what are our best opportunities for improving these forecasts along this forecast chain. Clearly, issues related to radar data analysis are essential for the quantitative precipitation estimates, and assimilation of very high resolution, very high frequency and time information is important for the short-term forecasting of precipitation. We've got to make some improvements in those areas. The HER group over at NOAA obviously is doing a lot of work in this area as well. We haven't had a chance to run those forecasts through. There's, I think, some evidence that those forecasts are quite a bit better than what we're seeing from the North American model. But I think still there's a lot of work to be done in that area. QPE issues, we talked about those. What are the existing QPE products? There's a lot of uncertainties, and validating these in a really quantitative way is going to be difficult because of the extreme nature of the event. The QPF, like I said, we captured a lot of the large-scale features, both in time and generally in space along the Front Range in Colorado during these couple of days. But the intensity patterns were largely lacking or inaccurate, and the localization of that along the mountain front and along the Front Range canyon systems was problematic. From a hydrologic prediction standpoint, obviously there's some fundamental problems that we have in dealing with the uncertainty in the precipitation estimates and forecasts, and those have a profound impact on what we can do with the hydrological simulations. That said, this wasn't just a precipitation intensity problem. As Rita mentioned, most of the intensities were light throughout this event, light to moderate. And what this meant was the ground was getting saturated. A lot of the shallow aquifer systems really started contributing to these stream systems. And modeling those kinds of processes, those subsurface processes, is very challenging for hydrologic models. And so there's a lot of work to be done in the hydrologic prediction area there. And a lot of what I showed even in our own model, even though we were mostly showing storm flow, we really did a bad job of predicting the recession parts of those flood events, of what happens 2 and 3 days later. And that has a very big impact on what happens downstream to Platteville and Kersey and Julesburg and all the other communities that ended up getting flooded later on. Okay, last thing. This is just the overall schematic then of the hydrometeorological prediction system that we're working on. And so as we've talked about today, we're bridging a lot of these different elements, ranging from observations down to analyses and doing assimilation at various points in this forecasting chain to focus on land surface and hydrologic data assimilation as well as atmospheric assimilation. And then pushing that through the short-term forecasts, whether they be nowcast systems from more extrapolation-based models or full physics numerical weather prediction models. And just to wrap up, this is essentially what the STEP program and its collaborators at various universities and other federal labs are working on. And hopefully we can use this terrible event as an opportunity as we move forward. Thanks a lot, and I think we'll all be happy to take any questions from everyone.
Thank you very much. I'd like to ask the speakers to come forward, and then we'll take questions. We're going to pass the microphone around. If you have a question, please use the mic.
So it seems to me that the critical information then is what kind of relationship should we use for the estimation of the rainfall based on radar data, and then the natural question is, should the differential reflectivity data help to guide the selection? And I think that this basically calls for for applying this kind of data sets more routinely, because I'm assuming it's not being used, as you guys have to switch from one relationship to the other just for this specific event. So that's something that should be emphasized, I think. That's one of the lessons that one can learn from this event.
Yeah,
So it's just a comment more than a question.
do you want a response?
I'll just respond. The dual pole products, they're fairly new, so the office and the Weather Service in general is still in the kind of learning experience, and so I think those will be used more in the future and maybe replaced as the ZR changes. The other thing is when you have warm rain processes, it's usually low centroid storms, so as you're getting distant from the radar, you're looking over the top. It doesn't actually matter what ZR you're using at some point. You're going to be missing some of the rain.
I think one question and one comment. I was surprised to see the big difference between the radar gauge corrected precipitation and the tropical storm precipitation. Is there something wrong with the rain gauges, that the radar is not corrected well enough and that the tropical even shows far more than the measurements? Because you would expect with a gauge corrected radar measurement that you would be closer to the real values. That's the one question. The other one is just in terms of the synoptic overview. I think we didn't talk a lot about that, but when I was in Seekers, there was a tremendous flow of moisture from the North American monsoon into this area previous to the system development. And I think maybe interesting to analyze how that really impacts and provided a lot of moisture that you had in the system. Is there any precipitable water anomalies and those kind of things that you had during this event? I haven't seen any soundings, but that would be interesting to look at that. The other thing is tropical.
So many of you either watched online or attended the NOAA Series CU panel meeting that was a week ago, something like that, last week. Time's going very fast these days. And they produced this figure, which was, looks like it was originally developed by the Weather Service to look at what were the precipitable water values that were generated from this event versus historical statistics. Okay, and so what you're looking at here is monthly plots of precipitable water, all right? And then these are different sort of terciles, or quantiles, sorry, of that information, and then maximums and minimums. This is what was observed on September 11th of 2013 of this year. So clearly a record for September, and really up here near the maximum values ever observed during the core monsoon season in this area, which is late July and early August. So this was a wet event.
And then as far as the rain gauges, the stage 4 products probably were not using the COCORA stuff that I showed you. They were probably using the automated gauges available at the time, which was far fewer than what you saw in the analysis I showed.
And probably have a low elevation bias too.
Yes.
Could you please remind us, Dave, what the QPE and the QPF stand for?
Yeah, so QPE is quantitative precipitation estimate. That's what we observe or we estimate from observations of some kind, be it a radar, satellite, or gauges. And then the quantitative precipitation forecast is what we predict will happen. Comes out of the models. Yep.
Seth?
Somebody want to pass it back to Seth?
Pass the microphone backwards.
Two quick questions. One, first one's probably for Matt. Where does the total rainfall stand in relationship to Colorado history? Has anything ever been recorded that's even close to this as far as a 5-day or 7-day total? Second one, coming into the event, were there any models at all that were running that even got close to indicating that we were going to have some sort of epic event? Just thoughts on those two questions.
So the first one, the daily record for Colorado was down, I think, in Holly, and it was over 9 inches. So we were close, but didn't reach it. But we're still analyzing because it appears there may have been some 10-inch reports daily. Now, I don't know about the monthly yet or the weekly. Nolan's working on that. But Boulder had 18.16 for the month of September. The previous record for any month, May of 1995, was 9.59. As of this morning's rain, we're up to 32.04 for the year. The previous record was 29.93.
Still rain.
Linda?
So, Jamie Wolf should probably answer the question about the model, but because she heard the briefing from NCEP right after the flooding event. But what I understand is that the fire model that was zoomed in on this region, a 1 kilometer, is it a 1.33 kilometer model, did seem to capture at least the intensities. I'm not sure the placements or anything about that, but so there is hope that we can actually reproduce it.
I want to answer from the forecast perspective. Having talked to the forecast office, the models gave general guidance, just like Jenny and Dave mentioned, so they knew it was obviously going to be a prolonged rain event. But what was not captured and what they didn't expect was the big jump in the precipitation amounts, and that wasn't captured in the models that they were using. Yeah.
Okay, it looks Linda, and then one more, and then we'll call it.
So you just answered part of my question, but I kind of wanted to go a little bit forward beyond what this talk was about, which has to do with, of course, why there was so much damage and how much of that, for example, we know the forecast was off in an important way that would have been very difficult to get. But beyond that, what else accounts for it? In other words, some events are so extreme, I don't think necessarily there's much of anything we could have done, and that you really don't often adapt to a 99.99th percentile event. And so the point is, was the region underprepared, or do extremes happen and you have the forecast error, okay? And you have the fact that maybe it really doesn't make sense to develop systems that are resilient to such an extreme event. So I'd just be interested in your opinions about that.
Linda.
What, Dave?
You make life so challenging sometimes because you ask hard questions. All right, this is the plot which comes from the NOAA Hydrologic Design Center in talking just about the issue that you raised. And what you see here is the 7-day rainfall annual exceedance probability. And outlined in the darkest color blue here is a 1 in 1,000 probability, 0.1%, often referred to as the 1,000-year event. Do we want to invest in infrastructure to prepare for this kind of thing? That's probably not up to us to answer that societal question, but we can certainly try and make some progress on saying how unique was this combination of events and what other things could be done to provide valuable information during the event that at least, if our infrastructure is going to be damaged, at least can help save lives and expedite things like emergency services, evacuation, so on and so forth. So I don't think we can answer the question that you asked fully. I think that involves a much broader societal discussion. But I think we can continue to make progress on our forecast systems. That said, personal opinion, you know, we've had big front range events before. This happened towards the shoulder season with tropical moisture helping. If this happened in the early summer, if we got an incursion of tropical moisture and the streams were already high with stream flow, we could see flow values like this again. That's not that unrealistic. So yes, the rainfall was very uncharacteristic, particularly for this time of year. But in several of these systems, like Matt mentioned already in Boulder Creek, the flow wasn't necessarily that uncharacteristic. So we should be aware of that. That one? Yeah. Yeah. This is from the National Weather Service. They've put out a really nice PDF briefing on the event. Covers a lot of good statistics. So.
Let's take one more question.
Could I just follow up really, really quickly? It's very short. Very, very short, but it's critical.
I'm late for a PhD exam.
Yes, yeah. So, improved forecast, great. Let's say the forecast has been accurate. What difference would it have made in terms of warnings and what people would have really done?
Where's Eve?
Because
Yeah,
that's
for
really a very,
that's
it's a
right.
critical question.
Yeah, again, I think for the communities who were impacted the most by this and the most tragically, I don't think we could have done anything to save their property. But hopefully we could have given them more warning to save themselves and a few of their most precious assets, and to get them to a place which would have been much easier for the emergency response system to help take care of them. But that's, yeah.
Good question. Last question.
Okay, that was a good prelude to this one, which is how much warning did the people in eastern Colorado have? I mean, it seems like they should have had more warning given, that it was a couple days later that they got flooded.
So I believe you're referring to, say, the flooding down the South Platte River?
Yes,
Okay.
along the South Platte.
So we're talking about the large river flooding. The reason I clarified is because there was actually a lot of heavy rainfall out there which produced flash flooding. Again, I think that would be a question of mobilization. From what I looked at, most of the large river forecasts for the main stem of the South Platte were actually pretty reasonable, because it was, by that time, already a fairly well-tracked event in terms of being able to be monitored as these flood waves came out of these canyon systems and converged into the South Platte River system. And the river models that the National Weather Service runs typically do pretty well on larger river systems. They're really designed for that kind of implementation, more so than the small canyon flash flood system. That said, that was a lot of water, and it covered an area that was quite wide. And as in terms of not many people died in those areas, but a lot of property was damaged. I don't know if you could mobilize that property out of those floodplains. So then it becomes a zoning issue after that, and it was just tragic. So I think the large river forecasts were decent, but given the magnitude and how broad scale that event was and how much area it covered, I'm not sure there was much you could have done to protect property there either.
Can I just add one thing? The Weather Service does have an assessment team that's looking at the warnings and the lead times. It's going to be delayed now, obviously, because of what's going on, but they do have a team that's going to look at that. I think one of the questions that they'll look at carefully is the fact that there was no flash flood watch, the predecessor to the warning, because emergency management tends to use the watches to really get staged and ready for these kinds of events.
Well, I'd like to thank the speakers one more time.